Welcome everybody. Thanks for gathering with me today around the virtual telescope, so to speak. We're going to go into a paper. I've got about 3 or 4 of them that I've gone through lately. Just want to kind of update a few of them. I think they're kind of cool. So the mystery of a Type IIP supernova. In this case specifically, I found a paper. It talks about the mystery of SN 2024 ABFL and what we've learned about supernova from it. So you can see, and we'll talk about this in the paper as I go through it and what my review of it. This was a supernova in 2024 that exploded in the galaxy NGC 2146. You can see it in the image here. It's they've identified the supernova. They've put a little hair target on it and shown you where it happened within that galaxy. So I've shared multiple times now that supernova are the deaths of massive stars, but they're far from uniform. There's all types of variety. A Type IIP supernova, we call it SNe IIP, are the most common variety in the universe. They're known for a plateau in which their light curves where they remain at a constant brightness for months. Here you can see the different types, and these are just estimated curves. They can vary a little bit up and down, a little longer, a little shorter, but anyway, this just kind of shows you a visual of the different type of light curves we see with supernova. As a reminder, a Type IIP, the plateau is this dark blue right here. It's the most common core. The plateau happens because hydrogen is in abundance in the expanding shell and it stays ionized for months. It keeps the brightness steady before it finally cools and fades. In a Type II linear, Type IIL, which is the light blue, you can see it peaks quickly, but then it fades off. It doesn't have that plateau. And the reason it doesn't have that plateau is most likely the star has ejected most of the hydrogen before the explosion. So there isn't enough material to sustain that holding pattern of brightness, and so the helium fades a lot quicker than the hydrogen there. Anyway, you can see Type IIb, that is the pink one right here, and the cyan. And these are shapeshifters. Through the eyepieces, they start out looking like a standard Type II. You can see that. They come up and they're peaking. But as the shell expands, the hydrogen just appears, and the helium becomes the dominant feature in that one. Okay, Type IIN narrow, that's the green one in the chart. These are particularly messy explosions. The N stands for narrow spectral lines, which tells us the ejecta as it comes out is hitting a slow-moving cloud of gas the star blew off years before it died. And there you can see it peaks. It holds a little brighter than normal and then fades a little more quickly. However, for Type IIP supernova, the physical reasons behind the diverse explosion properties such as energy and brightness remains a major question in astrophysics. This paper, and I've linked it here, so if you go to EadsyAstronomy and Patreon, you can get the link it takes you directly to the paper. You can read it yourself. Investigated SN 2024 ABFL, low luminosity supernova, like I said, that happened in NGC 2146. And it offers a rare smoking gun because they were able to go back and identify the progenitor itself and detect it. So they identified it. That before it blew up, as they looked at pre-explosion imaging, that it was a red supergiant. No surprise there. But by analyzing its brightness and colors, they estimated the initial mass to be greater than or less, equal to or less than 15 solar masses, and that's on the low end of the type of star that will end up going supernova. Low luminosity long plateau brightness, SN 2024 ABFL, was relatively faint for a supernova with a peak absolute magnitude of visual of 15 mag. Duration, it exhibited a remarkably long plateau. It lasted 126.5 days. It suggests that a large hydrogen-rich envelope was present at the time of the explosion. The physics of it, the math of the blast, so to speak, if you're interested in it, I'll go really quick. Ejecta mass, it put out about 8.3 solar masses of material into the interstellar medium space. Kinetic energy, 0.42 pho. Pho is a unit of energy equal to 1,051 ergs. This is quite low compared to most supernova. And then radioactive nickel, they estimated only 0.0009 solar masses of nickel was produced. Since the radioactive decay powers the later stages of the supernova glows, this low amount explains why the event faded so quickly after the plateau. So it hit, spiked, it had that plateau like we showed, but then instead of slowly going, it really crash dived. Spectroscopic oddities. The spectra mostly looked at the typical SNe IIP. The ejective velocities were much lower than average. However, at the later stages, they found a high velocity hydrogen alpha absorption feature moving at about 4,000 kilometers a second, likely caused by a plume of matter shot out from the inner parts of the explosion. Evidence of the circumstellar material, or CSM, interaction, meaning the shock wave was hitting gas that the star had shed before it died. Why does it all matter? SN 2024 ABFL is a benchmark case. Astronomers could see the star before it died and then track the explosion in detail as it happened and afterwards. It confirms the link between low mass red supergiants and low luminosity, low energy type IIP supernova. This helps us fill in the map of how different types of stars produce different types of cosmic fireworks. And I'll have a post that will allow you to kind of start to explore some supernovae as they happen, and you can actually track it for yourself. And even though professionals will probably label it before you, you'll be able to track and just kind of confirm for yourself what type of supernova you think it is. Thanks for joining me. Hope you have clear skies. Hope you enjoyed the new moon period. We'll catch you next time at the scope. Have a good one.